Hello, Mr. Dobson here, and welcome to my third video on gravitational fields. This one is on gravitational potential. So in the first video we looked at some GCSE concepts. We looked at G, the value of gravity on Earth, or the surface of Earth. What we mean by the value, mean the force on every unit of mass, so force per unit mass, force on every kilogram of our bodies at the surface of the Earth. In the second video we looked at Newton's law, the law of the force between any two masses. So even the tiniest little atoms, the force between any two masses due to the strength of gravity and the distance between them. Then at the end of that we managed to sort of combine the two. We changed this for a big M, this for a little m, to designate a massive mass and a small mass like us standing on the surface of the Earth. When we did that, and then we took the M over to the other side, we end up with this equation here, which is called the magnitude of gravitational field strength in a radial field. Basically, it's G for any planet. So it's the value of gravity, or the force per unit mass, on every kilogram of mass in our bodies for any planet. This is more generic because now you can choose the mass of the planet, you can choose the radius of the planet, so it doesn't have to be for Earth. Okay, so gravitational potential. Well, first of all, we actually don't want to think about that. First of all, we're going to think about the energy changes when we move something up in a gravitational field. We have some concepts from GCSE level. We know that if we have a surface here, we have an object on the surface of mass m, and then later on we move it up. Okay, we move it up a height h. Now at GCSE level, we may have actually considered this not to have gravitational potential energy down the bottom here. Often that will be the case. We say things that sort of can't fall, don't have gravitational potential energy. It's a simplified answer. It's true of the system. If you think of something like a pendulum at the bottom of the swing, it can fall no further. So as the system of the pendulum, you could argue that it has no gravitational potential energy at the bottom of the swing, but we do know if you just let go of the string it would fall, just quite the same as that this, if the ground was to suddenly disappear here, it would fall. Really, it has got gravitational potential. There's actually a force downwards still on this ball coming from the centre of this mass here, going downwards, and that is weight. But the only reason it doesn't fall is because there's an equal and opposite force being provided by the surface of the floor, or whatever it is, upwards, cancelling it out. So it does actually have gravitational potential, the energy at the bottom. So we can call this EP. Okay, now we know that if we was to lift the mass, we'd have to do some work. We'd have to lift that mass up. It would have gravitational energy at the top. The gravitational energy it'd have at the top we might call EP prime, as a new value of gravitational energy, gravitational potential energy. And we know that we can actually calculate that. If we want to know what the gravitational potential energy it has at the top is, we may have used this equation. EP equals mgh. Now that's fine. A little adjustment for the fact that for what we know now, because we're not considering this to be zero at the bottom here, actually we're looking at the change in gravitational potential energy from here to here. So rather than calling that EP prime or something like that, I'm actually going to call it delta EP. So delta EP equals mgh. This is the equation that we would have had at GCSE level. And what it means is that as I lift an object, its gravitational potential energy will go up. So it will change, you get a change in gravitational potential energy, and that's equal to the mass of the object times the force of gravity at the surface of Earth times the height. This equation, actually, if you know your physics really well, you can actually rewrite this equation and see that it's just a form of a very, very famous or a very well-known equation, because a change in potential energy, a change in energy, is also known as work. And the equation for work done, is force times distance. Have a look what we've got here. Oh well, hold on. This is work, this is a change in energy, same thing. this is height, which is actually a distance. So they're the same thing. Oh, F equals, or W equals mg. So this is a force, and we can see it is just a rearrangement of the equation of doing work. That a change in energy or work done is equal to force times distance. Now, this therefore, the reason this is true, why we can say this is true, is because at the bottom, if I want to lift it from here up to here, I have to do work. I have to put energy into the system. And whatever energy I put in to lift it from here to here, because of conservation of energy, has to go somewhere. And where does it go? Oh, it goes into new gravitational potential energy at the top. Obviously, in real life, there might be some loss to friction and things like that, but we consider frictionless and a simplistic version here, so that's fine. So what that means is that all the energy I put in to lift it from here to here will become, or you have the equivalent extra energy at the top here. So we can actually equate the two. We can say whatever work I do to lift from here to here will be the same as the change in energy from here to here, which is why they look so similar, because actually this is equal to this when we lift an object. So that is the GCSE recap. That's what we know about the energy of an object when we lift it in a gravitational field. But there's a problem. Let's look at this here. I call this the change in gravitational potential energy here is equal to the mass times the strength of gravity at sea level times the height. Where's the problem? Well, if I'm going to change the height, they're no longer going to be at sea level, which is a bit of an issue. Now, in a future video, we'll look more closely into this, but just to give you a rough idea, if I have a planet, big M here, and I was to want to put things in orbit around that planet, so I might put something here or here, as I'm moving away from that planet, the actual force of gravity drops off as I move away. If I was to draw a graph of the strength of gravity, as I move away, if this is the radius of the planet here, then let's say at this point it's 9.81. This is the G, let's call this Earth. As I move away from Earth, this actually drops off, and it's an exponential curve. So it's dropping off in a shape like that, which means as we move away from Earth, the strength of gravity on every kilogram of our mass reduces. So we have a problem, because this value is going to change as this one does, and we haven't got a dynamic equation here. There's not differentiation or anything like that, so this is not designed to change. This is designed to be a constant. Now you can actually just work out a new value for G. We could just use this equation here that we learnt before, and say, for instance, we could, for this point here, calculate a new value of G, call it G prime, and do a calculation there. We could put in the new radius of this distance here and get G prime prime, etc. If we just change the radiuses each time, we'll get from this equation that we learnt last time, we'll get a new value of G out every time. So we could actually work out what G is there, stick that in this equation, and that's okay. Except this is a dynamic thing. This is something that's changing. We're looking at what happens as we move out, which means G is changing constantly. So unless we was to calculate G, or the change in G, at every point along the path of it moving out, we have a bit of a problem. So we really need an equation that allows G to change. Now you might say to yourself, well, why do we even bother with this then if this doesn't work? Well, because actually it works very well. But it only works very well if H is small. And by small, we mean small relative to the radius of the Earth. Because the radius of the Earth is a very, very big value. And you have to get to a significant distance away from the Earth before you really start seeing a drop off. I know this is an exponential graph. It looks like it drops very suddenly, but these are very big distances. This is in multiples of the radius of the Earth. It's very large. As you can see, the radius of the Earth is in the it's in meters, so that's in the megameters range, in the thousands of kilometers range. So we're talking thousands of kilometers distance in here. So this small distance here, you know, anything less than 1,000 kilometres is going to be insignificant compared to this big difference. We're going to move very little far out on this chart. G is not going to change significantly, and therefore, providing we're only moving relatively small heights, bear in mind the highest building on Earth is less than a kilometre, this is fine. There's no problem. G is not going to change enough to make the answer significantly different. In fact, technically, G is a little bit different depending on where you are, because the surface is not very often at sea level unless you're standing on the sea. So it's all slightly wrong, but the value changes so insignificantly we don't need to worry about it. So we can use this for very small values of height. But once we get to a height that's relatively big to the mass of the to the radius of the Earth, and by that we're talking something in the region of 1/10 of the radius of the Earth, so something in the region of 100 kilometres or something like that, then we start seeing a significant change in G, and this no longer really works. So we need a new equation, an equation that will work to get us from to be able to calculate the change in gravitational potential energy as we move far away. And we need that because we like to put things in space. We like to put satellites up there, and we have moons orbiting us, so we need to sort of be able to work out what's going on there. Plus we're orbiting other things that are important too. So we need a new equation. This is actually easier than it seems, because we've already said in a previous video that this is a version that's only true when we do 9.81. It only works for the value at the sea level of Earth. But this version is more general. This version doesn't matter because R is taken into account. So we can actually consider a change in radius, and M is also taken into account, so it works for any planet. So it's a general formula. So if we were to use that instead of G, we might have something that's much more general. So let's have a look at that. If we want to therefore work out the work done or the change in gravitational potential energy, so that's delta EP, which is equal to W, which is equal to force times distance. Okay, so what do we know? Well, we know that our force is equal to our force will be equal to mg, so that's that. But the g we're going to use is the more generalized formula, so it's going to be m big G big M over r squared. Okay, so we've got that. We now need to combine it all together. We need to think of the distance value. Before, when we did it, we used height as distance, but of course height's actually telling you really a change in radius as such. It's the difference between where we were and where we're going to. It's actually not a measure of how far we are from where the gravity is coming from, which can be considered to be the centre of the Earth. So H isn't actually the best value for us here. It'd be much more useful to use R and talk about how far we are away from the centre of the Earth. We use R rather than D because it's a radial object, it's a round object, so we use R. So in that case, bringing all these things together, we can say that the change in gravitational potential energy is equal to the work done, which is equal to force times distance. The force would be this bit here. Now I'm going to move the little m to the other side because we're used to seeing it there. It just generally gets drawn that way. So we end up with G big M little m over r squared, okay, times the distance, which is r. And some of you eagle-eyed have probably spotted it. We can cancel them out, and we therefore find that the change in gravitational potential energy, or a new equation that works no matter how far away from the planet we get, is G M M over R. Now what do we see? We see this is very, very similar to the original Newton equation. If we go up to here, we had G big M, little m in this case, over R squared for force, and we find that for energy it ends up being G big M, little m over R. So the difference between the force between two objects, so if I just make that clearer, maybe I'll draw that to the side here. So the force is big G big M, little m over R squared. That's the force between a large object and a small object because of the large object's gravitational field. We can see that the change in potential energy looks exactly the same, only the bottom is not squared. It is not a square of the radius between the two objects. It's also worth pointing out that I sort of fudged this ever so slightly because I've ignored the fact that really this was considered, we said this is actually a minus. It doesn't really have it in the A-level textbooks. It's considered a minus. This too would be considered a minus because the direction of the force here is in opposition to the direction of the radius, so it's minus. We saw that in the previous video as well. The minus is just because it's a vector, so we have to consider a direction. We don't actually have to worry about it too much in our calculations. So we have this new equation. Let's highlight it here. Here's our new work anywhere equation for the change in gravitational potential energy for any distance from the centre of the Earth, given a big value and a little value. Now the problem with this is, it's a great equation, it's true, it works, and it's true all the time, unlike the equation that we had before, which was not always true. The problem is, it's a good equation, but it relies on little m. And because it relies on little m, it means that this value is different for things with different mass. So it's not a general equation, really, because it would be different for two objects that are different in mass. So it's not a generalised equation. We can make it a generalised equation, though. We did this before when we worked out this here. Okay, we took the little m to this side. We made it, because it was originally F equals big G big M little m over R squared. We took the little m to the other side, so it looks like this, and called it G, and then we had GM over R squared. We had it without the little mass value in there, so it's now general, and it's actually the force per unit mass. So that works quite well. It makes it a very general equation. So it'd be nice if we could do that for this, and we can do that. So we can actually take the little m to the other side, and we can have the change in gravitational potential energy per unit mass is equal to minus G big M over R. This is a general formula. That is supposed to be a G. There we go. This is a general formula, and it says the change in gravitational potential energy per unit mass. So what it means is, if I was to move an object, or if I was to be moved a distance r from the surface of the Earth, I would therefore have a change in gravitational potential energy for every kilogram of mass equal to whatever this comes out at. So this is a nice general situation, and it would make sense really if we could, before, when we had force divided by mass, we gave it a new letter, we gave it little g. It would make sense if we give this a new letter, the energy, change in energy per unit mass, or it's also the work done per unit mass, because change in energy is work done, and there is a letter we can use, and I hate it because it looks like voltage. It's capital V. So capital V is equal to minus Gm over R, and capital V is the gravitational potential. Now, There's a very horrible definition of what gravitational potential is. It's the work done per unit mass. So that's work done per unit mass to move a test mass or an object from infinity to that point. From infinity to that point is a horrible sounding thing, but in the next video we'll look at how gravitational potential works and why that's the case, and the fact that why gravitational potential is a negative number. Okay, but for now this video just showed us how we get there and what it is. Incidentally, if we were to put in the values of G and the value for M on Earth and the value for R on Earth, we actually do get a value. The value for gravitational potential on the surface of the Earth, so that's if R is at the surface of the Earth, works out at 6.25 times 10 to the 7 joules per kilogram. So it does actually have a value, and that's a minus value. Okay, so we end up at the point now where we have defined this equation here. Okay, now this equation here you can see is actually just a very slight rearrangement, because we actually said that V is equal to the change in energy of the work done per unit mass. This is a rearrangement like this one is, but for some reason here they've got it this way round, here they've got it this way round. There's no reason to have it one way or the other, but it's how to convert between the three values. This is the one we've managed to calculate here. So this is our new equation for gravitational potential, and this is what gravitational potential actually is. If you take the M over to the other side, it's the change in energy per unit mass. Okay, thank you for watching.